Introduction to logarithms, here we go. So we just talked about this exponential function. It has an intercept at y equals 0. Okay, not a perfect mapping of that function. But we have some points, -2, -1, 0, 1, and 2. This is 1/4, 1/2, 1, 2, and 4. This is an exponential function. Your basic exponential function, it has a base of 2, it has an exponent of x. Question, you probably can't see this if you're looking at the video, but it says, does this function have an inverse? There's something we didn't discuss when we were talking about inverses, and that is the concept of how do you create the graph of an inverse. And it's pretty straightforward, actually. If you draw the line y equals x, so if you look at this, hold on here, there we go. If you look at this green dotted line, this is what we call the identity line. This is the line y equals x. If you reflect a graph in that line, you get that graph's inverse, or that function's inverse. Okay? So in other words, you've been in the honors geometry, I'm sure you should probably remember this. When you do a reflection, you're finding the distance of each point to that line, right? Dropping altitudes and then recreating that on the other side. That's one way to create a reflection of something. So in other words, if we have this intercept at 0, 1, and I find this distance to this line, and then I recreate that on the other side, the inverse point would be 1, 0, right? And what you would get is all of these distances. Like if you recreate this point and you drop an altitude to here, you would see that alternative value down here somewhere, right? And we could draw all of these lines, all of these altitudes to the green line and show the mapping of these other points. But basically what you get is this shape. So you see how that is a reflection of the exponential function over that y equals x line. So this bluegrass, I've been listening to a lot of Avid brothers. This blue graph is the reflection of the red one. Therefore, this is the inverse of that, and this is what is called a logarithm. So when you look at, when you switch the domain and the range of this function to get the inverse here, what you would see is a table of values where these numbers, 4, 1, 2, 1/2, 1/4, and this is 2, 1, 0, -1, -2. Because we're using the range of the exponential function as the domain of its inverse, you can tell also by looking at the graph that this logarithmic function, y equals log base 2 of x, this is our inverse function of 2 to the x. It's log base 2 of x. If you look at this, the domain and range are switched. Bless you. Graphically, what's the domain of a logarithm function?
All real.
Not true. Not true. What is the domain? Look at the, go back if you want. Okay. What is the domain of an exponential function? All real numbers. The range is only positive values. So what is the domain of a logarithmic function? Only positive values. Remember, you guys, when we have an inverse function, we flip the domain and the range. Graphically speaking, how far to the left does this function go? Doesn't it look asymptotic to the y-axis? So it's not going to pass the y-axis. It's not going to include negative numbers. So the point we're trying to make here is that the domain is the range of the exponential function. The range is infinite. The range goes from negative infinity to positive infinity. A logarithmic function has a vertical asymptote, x equals 0, and it has an x-intercept of 1 comma 0. So if you're comparing this is some of the similar values that we had for the exponential function, but the domain and range are swapped. The x-intercept is the swapping of the coordinates of the y-intercept from the exponential function. And instead of a horizontal asymptote, we have a vertical asymptote. These are the defining characteristics of any logarithmic function. It doesn't just have to be log base 2, it can be log base anything. All right?